Part C.
No, it didn't cost that.
No, the question I gave you. The question I told you to do.
Exam question.
The exam question, yeah, did you do it?
I did except part 3.
Wait, you didn't do it.
I did part A and part 3.
Well, what was part C?
Pretty sure that's what it did in class, isn't it?
Part C was the Kirchhoff one, wasn't it?
Yeah, that's what we did in class.
That's why we started in class, at the end of the class, isn't it?
Yeah, that's
It's not that B6, right?
B6, yeah. You didn't have a part C.
Yeah.
Well, I think the second, I'm pretty sure this part C was a different question. Like, it wasn't a different question, but it had extra.
Yeah, no, part C I thought was Kirchhoff.
Yeah, it was I1, I2, I3.
Was it that? I1, I2?
Yes, I did the one you showed.
The one
Yeah.
in class, yeah.
Yes, the potential divider.
And then the...
So why did you not do C?
I don't know how to do it.
You don't know how to do C. I don't know if I believe you. You do know how to do C. You sure you don't know how to do C?
I'm sure. I don't know.
Abraham, did you try it? Oh, okay. Louise, did you try it?
I tried it, but I was, do you remember last time I asked you the question about in the laundry?
Yes, I remember, but I don't remember
In
what
the
you
last
asked
class.
me. Yeah, what you asked me. I don't remember.
Okay.
Was it this question?
Oh, really?
Yeah, we did this one.
This one.
Yeah, there.
Ah, this one.
Yeah, did you try to finish it?
No.
No, okay. This was part C.
Part B.
The part B.
Yes.
It's just part C's in a different page.
Yes.
Oh, what's part C then? Do you have it printed?
No, we didn't
Oh, I didn't realise it was on the next page. Let's have a look at it then.
Yeah, this is part B. This is part C has an I3.
Right, let's have a look here. DIFC, past exams, physics, book. A, B, they're talking about, there's no C, there's A and B.
Mentioned different things, sorry, because I definitely remember one of the I2, I3,
Oh, maybe I have the wrong file up there. Maybe I don't have 2014. Yeah, sorry, maybe I have 2013. Like this. No.
I remember one of I2, I1, I2, I3.
You sure that was a part C?
Yeah.
Are you really sure?
Yes.
Okay. I'll look at it next week when we do revision anyways, okay? I'll look at it next week when we do revision. Okay, so our last part for this semester, we're going to be looking at waves. Yeah, we'll get around to that. I don't think today. So, do we all know this word in English, wave? Yeah, Louise, do you know this word? Yep. So, what you need to know about waves are that waves come in two types. So the first type is called longitudinal. I'll write that clearer. Longitudinal. And the second one is transverse. So Louise, when you did this with your hand, that is actually this type of wave. That's called a transverse wave. So what you did with your hand when you went like this is a transverse wave. Longitudinal is difficult to draw. It's like slinky. It looks like this. You have something vibrating, and then the close together, and then further apart. And it's hard to draw. You really need it to be animated, and I wonder if I can get an animation of it. I should be. So with longitudinal, the wave is moving like this. Well, not so much back and forth, but it's moving out. Whereas with transverse, it's going up and down. So transverse is up and down, whereas longitudinal is just kind of vibrating out like this. If I can get a video, I'll try and show you an animation. Maybe an animated GIF or something. It hasn't. We have internet. Let me just switch. Yeah, actually, I should really use this for internet because it's better. But this is not on the video now. Yeah, so you'll need to. Yeah. Yeah. Now there's a nice picture. Let's have a look here. What's a nice one? I guess here's showing the two types. I hate that. View image. Too small?
Yeah.
Right. Can't see it. SPX. Where's the nice one? Yeah, they do this with. They do use a spring. Yeah, like here. The person's hand is shaking back and forth. These are all smalls. If I go to videos, maybe I can get a...
Yeah,
the Slinky. Oh, this is in Arabic. Or is there somebody signed in?
Oh, yeah.
There we go. Can you, I wonder will they slow...
I think it's
They'll slow it down.
just like between Argentina and
Slow-mo. Yes. That's not slower.
I think they're just kind of like showing it now.
Faster. But you can see it's rushing down the spring. Maybe we can find this dude. I don't even, yeah, can you see it moving through the wave moving like that? Yes. But I wonder if there's both. This is only 7 seconds. Yeah, that's what I was looking for. So you can see, let me play it again. The longitudinal one, it's like a pulse running through it. And then with the transverse, that's the one you drew, Louise, the one going up and down. So I hope you can see the differences with this video. Yeah? But now we need to try and put these into words, because in the exam they might ask you to describe the difference. So does anyone feel brave enough to try and describe the difference in words? What do we think?
Transverse waves are waves that go parallel to the movement of the waves. Like the amplitude of the waves is moves parallel in that order. Travis waves of...
Let's give someone else a go too. Anyone else want to? Simple English first, and then we'll build on it. So simply first, what's the difference here? Simply describe the difference. Don't be shy. Abraham? I don't know, simple description. Don't worry about being right or wrong.
They have empathy, but don't really they don't have.
Well, no, I understand what he's saying. We haven't done the word amplitude yet. But just, imagine you were explaining this to Stephen B. Alright? So,
up and down.
yes, okay, good. So transverse goes up and down, and then longitudinal goes back and forth. So we have up and down and back and forth. So now we'll make it more technical, okay? So what's happening here is, you can picture this is moving to the right and this is moving to the right. In this example, the vibration is in the same direction as the movement, whereas here it's moving up and down. That's perpendicular to the direction. You see, this is moving right, but this is going up and down. Whereas this is moving right and also parallel, yeah. So the difference is the difference between parallel and perpendicular. Now there's a really fancy word here, and it's a very, I wonder if anybody knows this, but you said, Ugo, that the wave moves, but we don't like the word move because the wave is moved in two ways. For example, if I take my rope and go like this, you see it going up and down. Yeah? But it's also moving from the start here to the end of the table. So there's actually two types of movements. Does that make sense? I can actually, if we go back to the video here, if it hasn't started playing something else, I closed it. Yeah. So when I flick it here with my hand, there's a wave that moves through it, but also as it moves, it goes up and down. So we don't use the word move because it's not clear. So does anybody know another verb or noun that means, another verb that means move? No?
Sure, vibrate.
Yes, go ahead. Transfer is good, I like it. So we could use transfer. So we could say, we could use transfer. And I will use transfer, but there's another word too. Another verb for move. Do we know it? Not quite move. Anything else? No, I would maybe really only expect Ugo to know this, but
Yeah,
you
but
don't.
I can't, it's not flashing.
I can use the first letter.
Okay.
That's P.
E.
P. Yes, P. P. Progress? Not bad. Like progress. Pivot? Oh no.
I'm getting way off there.
No, not progress. The progress was very close. It's not progress though.
Progressive.
Not progressive.
Nothing fucking up.
No, I need to check the spelling, but I'll type it in here. I hope I spelled it right. Propagate. Yes. Does anyone know this word? Anyone have got this? Okay. Propagate. Have you heard this word before? No. Propagate is a word that has two meanings, one in biology and one in physics. So the biology definition is on the screen. In biology, propagate means, the animals have children and they have children and the population gets bigger. In physics, propagate means the wave moves. And the movement is the movement along this direction. So when we say the wave propagates, we talk about where the wave starts and ends. It doesn't mean anything about the movement like this. Okay? Yes? So you understand? Propagate? Yeah, so Well, you should write that word down. Maybe you even want to look it up in your dictionary later, okay?
So basically movements in the gate to the vertical axis.
So,
No, the horizontal.
in the horizontal for this case here. Have you got that?
So the rate is,
Yes, just for the waves. Yeah, we just use propagate as a verb for waves. Yeah. So if I go back here, so propagate, I'll give it to you in a sentence. For longitudinal waves, we say the wave, like if I call this here A, B, we say the wave propagates from A to B. Likewise here, we say the wave propagates from A to B. That's how we use propagate. Do we have a verb for the other type of movement with the blue arrows? So propagate is for the red, and what about for the blue that describes how movement, like this or like this? Do we have a verb for this? I used it earlier today. It begins with a V. V.
What's the other verb in?
Not verb, no. Do we know? I think someone knows this. It begins with a V. And it describes this type of movement. Vibrates, yeah. So we would say in the first one, the wave propagates and vibrates in the same direction. Whereas in the second one, we say the wave vibrates perpendicular to the direction it propagates. Okay, so I'll write that down. By the way, there are many ways to write this definition down. So, I could give this definition using the verb energy, not energy, transfer, and then also energy. I feel the words I use is the simplest definition I can make, okay? So here we say the wave propagates and vibrates in the same direction. And then here I can say the wave vibrates perpendicular, should I say perpendicularly? Which is more correct with the Y, I suppose. The wave vibrates perpendicularly to the direction of propagation. You will need these definitions for the exam because they sometimes ask you to explain the difference or to give the definition. There are actually other words that can be used here that mean the same thing. So I say longitudinal, but I could also call it a compression wave. I can also call it a progressive wave. So there are actually other synonyms for longitudinal. But there aren't synonyms for transverse. We just call it transverse. I can't think of any synonyms for transverse.
Stationary?
No, not stationary, no. No, I think it is just transverse. Well, actually, I checked it. No, just transverse.
What's a transverse wave?
There's a transverse wave.
No, like there's a different, within a transverse wave or something else.
Don't know what that is. Transverse is the only word here, okay? Longitudinal, compression or progressive are the other words. Let me write that, I was beside you. So we can also call this, a progressive, or another name for this type of wave is a compression wave. Okay. So some more vocabulary now with waves. Can I scroll down? Not yet? Okay. Yeah? So if you look here, here is, which wave is this one? Transverse. Now, just so you know, when we draw our longitudinal wave, we can actually draw it as a transverse wave as well. So like for example here, it's very intense. So we could draw the hill here and then it gets flattens out here. But don't worry about that. All I'm saying is we can draw both waves with this diagram. Okay? Vocabulary now. So this part of the wave has a name. This distance here. I think you said it earlier, Ibrahim. What's it called?
Amplitude.
Amplitude. Very good, yeah. So that's one word I want to tell you. Amplitude. What else do we have? Oh yes. Now, the wave starts here, goes to maximum, goes to minimum, and then gets back to the start. This distance here has a name. Not quite. Wavelength, yeah. So we call this one wavelength. The length of the wave. Now, when I talk about the speed of the wave, do you think I'm talking about how fast it propagates or how fast it vibrates? What do you think I might be talking about? Propagates. So when I talk about the speed of the wave, I'm talking about how quickly it propagates. Okay? So speed is speed of propagation. Now, do you have that? Yeah. Now I need to go back to I really need to go back to my animation here. What did I type in last time to get this? L-O-N-G, got my letters mixed up. I think it was this. Which animation? Maybe this will do. There we go, yeah. So there's longitudinal. So when we talk about speed, we're talking about how quickly this piece is moving, okay? And then transverse, when we talk about speed, how quickly it's moving along here, see? See, there it is moving there. Okay, this one's a nice little video. Good. Now, next one I want to do is period. So period is the time between, or how long it takes the wave to complete. So what we do for period, imagine you're standing here at the W. So imagine you're here, okay? So we're standing here. So we start counting at the first one. Okay, so we go 1, 2, 3, 4, 5. 5 seconds is the period here. And let's do transverse. Okay, so we're standing at the W. 1, 2, 3, 4 seconds. Do you understand what I'm doing there or not? I'll do it again, just one more time.
See the one people can pass the WAV?
Yes. The time for one piece to pass the. We'll go with W. So I'll leave the mouse there. Okay. So wait. Oh, it's gone. 1, 2, 3, 4 about. Okay, so let's do the next one. Okay, so wait till we get to the W here. And start. 1, 2, 3, 4. So this is called a period. Okay. So the period. Now, Louise, you use the word piece, which is good, but we have a different word. Same meaning, but we don't use piece because piece is too informal. We use the word cycle. Cycle, yeah. So we can say the period is the time of one cycle to complete. Okay. Okay. Next word is frequency. And you can think of it as a formula. It's 1 over t, which the unit, what would be the unit here? Yeah, in fact I think we did this one already. Frequency is 1 over the time, but what's the meaning of frequency? What does it mean, frequency?
The amount per second.
Yeah, frequency is the number of cycles per second. So in that video I showed you, how many cycles did we have per second? Yeah, we didn't even have one. How many seconds did it take for one cycle? 4. Remember, 4 seconds. So that means per 1 second we only have 0.25 completed. Yeah. Now if we go, oh, what's this next one? Where's that video with the guy, the physics guy, the really fast one?
It was in
I clicked this and then it was on the side, isn't it?
No, I think you go up, it was because he's talking on waves again. I believe it was the circle rounds.
Where's my friend gone? He was Penn State, wasn't he?
Yes, I'm fair. Pretty sure it's from Google we found it.
Yeah, that's what I did. Here, let's watch this one.
Yeah, mechanical waves. Which one's that?
I'll get to that now. This isn't even animated. Maybe I can show you with my hand. So for example, if we start here, okay, so the waves come up, down. So what we do is we count how many cycles go past in 1 second, okay. So on the video I just showed you, it took 4 seconds for it to pass through. So in fact, if you use your formula here, what's the frequency? It's 1 over 4. We only get 0.25 waves in 1 second. Okay. Now, what would it look like if the frequency was 2? If it was 2, that means we get 2 cycles per second. So if we're going really quick, if we're going like 1, 2, if we're moving really fast. Okay. Alright, next now, we're going to compare waves.
Well, which one's similar from mechanical?
Mechanical wave is just waves that have to do with mass being displaced, because we also have electromagnetic waves, which is for light. Sorry.
I remember that. I think there's something like here. Something else within it.
Yeah.
I just can't remember what it was.
Alright, next now.
Oh.
Yep. I don't worry about the spider. Where?
Here. Quizá tengo cuerda. Oh. Here.
Oh, where? Where?
actually in there.
What is she talking about?
Actually, the spike in there and then going down. I don't know why.
How you doing?
Wait, was on this table?
Wait, what's that on you there? There's no poisonous spiders in Ireland, so it won't hurt anybody, don't worry.
And that's Spider-Man powers.
Yes, Spider-Man powers. Right, okay, so I'm going to draw two waves for you here. So here's my first wave. Okay, and now let me draw the second wave. Okay. Now these waves look very similar, but you can kind of see with your eye, the second wave, the blue wave, is like it's in front of the red wave. So this difference is called, this has a name when we have waves, we call it the phase difference. So we say that these waves are out of phase. Out of phase means they don't match up. Like not in sync. The peak here is in a different place to the peak here. Okay, so we need some more vocabulary now. So I'll draw it here. Here's one wave, and here is the other wave. So you can see here, here's the top of that wave, and then here's the top of the second wave, and they don't match, and this distance here, this difference is called the phase difference. Now, we describe this as out of phase. Here's an example of two waves that are in phase. So there's my first wave. And then here is my second wave. Let's say it's a small wave. So notice here that the top here matches the top here. The bottom here matches the bottom here. The top matches the top. The bottom matches the bottom. Can you see that? So we call this in phase. There is no phase difference. This will become a very important idea. Okay. Can I scroll down? Yep. Okay, so there is an equation. Oh, I should actually, let me go back to my definitions. I should give you the letters here. So what letter do we use for frequency, do you think? F. Periodic time, T. Speed, V. And wavelength is this symbol called lambda. This is wavelength. Lambda, Greek letter. Okay. Oh, and what letter do we use for amplitude? A. Okay. Can I go down? So we have one formula so far, but you have this formula from mechanics. You knew this formula from mechanics. The formula I'm going to do now with you is called the wave equation, and it's a way of relating the V, the F, and the lambda. And the formula is not difficult. The the speed of the wave is equal to the frequency of the wave multiply the wavelength. Now, you can imagine that these waves, they have energy. For example, if I tie a wave to Louise and then I flick it, she will feel that. Yeah? So there's there's an energy with the wave. So if the wave is going faster, is that more or less energy, do you think? Well, it's more. And what about if the wave had a bigger amplitude, like if it was really big? You think that would matter too? Yeah, like I mean, think about an ocean wave. If the ocean wave is really high and it hits you, that's a lot of energy. Or if it's moving really fast, you know. So we can also think about waves as being like energy being sent somewhere as well. Okay. Let's have a look at some examples here. So we haven't actually given examples of waves, but I've just said one there. One type of place we see waves are in the ocean waves. But give me other examples of where you've seen waves. Where else have you seen waves? Light, yeah. Light is actually a wave, but yeah. Heat. Sound, I think. Heat, not so much, I don't think. I know why you said heat, because when I draw my heat, I always do it like this, but it's not really a wave. Sound is a wave, yeah.
The earthquake.
Very good, yeah, earthquake will be a wave as well, yeah. Yeah. Earthquake. Very good. Anything else we can think of for waves? Think about your kitchen. What do you use it? Microwave, yes, yeah, that's it. Well, see, this is not quite. I don't want to confuse matters. Microwave. Give me one more. Yes, X-rays, good. X-rays are waves, yeah. So let's look at an example with a sound wave first, okay? Anything else you can think of? No. Yeah, but that's infrared, radio. Actually, I hope maybe some people can see that there are two important differences here. Look at ocean sound and earthquake is quite different to light, microwave and X-rays. What's the difference? What's the difference between ocean? There's something in common with ocean sound and earthquake, and there's something in common with light, microwave and X-ray. Say again? No, not even that, which, might be true. Earthquake would be longitudinal. No, earthquake would be well, no, actually, I suppose it's both. No, it's not that. Something else?
Outside the threshold of...
No, not even something complicated like that. Something ocean.
You're wishing for
I'll tell you, if you look, ocean, sound and earthquake have something in common. For an ocean wave, you need an ocean, of course. For an earthquake, you need ground. And for sound, you need air. So you need a material. But for light, for microwave, and for X-ray, you don't need any material, any medium. Yeah, it could be in a vacuum. Ocean needs an ocean. Sound needs air. And earthquake needs earth. If you don't have earth, can you have an earthquake? No. If you don't have ocean, you can't have an ocean wave. But the thing that's strange about light, microwave and X-ray is for light, I don't need anything. I just need the light and it will come out. I don't need air, right? I don't need air. I don't need ground. It'll just come out. Okay? So we'll talk more about that actually later today. And you were asking me, Ugo, about mechanical waves. Ocean sound and earthquake are called mechanical waves because they need a material. Yeah. Okay, so let's look at an example with sound. Have you ever seen these little tuning forks used by people, musicians? You know what I'm talking about. You hit it on the table and then it makes the sound.
I'm sure musicians use them.
Oh, they do? Well, maybe they don't, but they use them to tune their equipment.
They used to, but they don't use them anymore.
Well, okay, maybe not
There's
anymore.
better ways to do it.
Probably. This makes a sound wave, of course. Now, the sound wave, let's say its speed is 350 meters per second. And let's say the frequency here is 440 hertz. What I want you to do for me is to tell me what the wavelength is. What is it? 0.8 meters. Will be in meters anyways. So we use the formula V equals lambda F. So we have 350 equals lambda times 440. So then lambda will equal 0.8 meters. Yeah. Now that's actually pretty big because 0.8 meters is about, about this much. So when I'm talking to you, the wave is quite, well, I'm not talking, when I'm using this here, the wave that it makes is quite long. Kind of a big wave, okay? Now, you all know what the word frequency means in music, do you? Like, how many people here play an instrument? Does anybody? Nobody plays an instrument? Nobody? No?
I used to sing, but
Sing? Okay. Do you still sing? Would you know other notes?
no.
No, okay. So if I said middle C, you wouldn't be able to give me that.
I wouldn't remember.
Okay, alright. In fact, with sound waves, the frequency, I wonder if anybody knows this. Well, if the frequency was bigger, how does it sound different? So here the frequency is 440. Let's say the frequency was 500. Or 600. How would that sound different?
Higher pitch.
Yeah, well, higher pitch. You know pitch? Higher pitch? Yeah. So I'll give you an example, okay? When Ugo is speaking, his frequency will be lower than when Louise is speaking. So what's the difference between the two voices?
Low.
Yeah. Low, yeah. So this sound of low is because of the frequency. When the frequency is low, when the frequency is small, it has a low sound to it. And then when it's not low and it's higher, the frequency is bigger. Yes, just like that, yes. So for sound, the frequency, you can hear it as the difference between a low or a high sound. Low pitch or high pitch is what we call it. So did you know this word pitch? Yeah, you know pitch? So if F is small, that will make a low pitch sound wave. And then if F is large, that's a high pitch sound wave. Okay. Right, can I give you another example now? A little bit more difficult, yeah? Can I go down? Yeah. So here we have something that makes a sound wave again. Maybe it's a speaker or whatever. And let's say the frequency is quite low. Let's say it's like 300 hertz. And then here is a microphone. So here is a speaker, and then here is a microphone. And then there's a wall here. And let's say the wall is 100 meters away. And let's say the wavelength of this sound wave, or well, it doesn't have to be sound. It could be whatever, light, whatever. It doesn't have to be sound. Whatever it is, it's a wave. Let's say its wavelength is. Let's make it easy. Let's say it's about, I don't know, 0.9 meters, something like this. So this wave leaves here, and then what happens is it hits the wall, and the wall is 100 meters away, and it comes back. So my question is, how long until the wave comes back and the microphone detects the wave? So in other words, I want the time here. I want the time for the wave to leave, hit the wall, and come back. So try and get me the time, and then I'll show you how to do it. Are you sure? No? What do you need first? The speed. So what's the formula for the speed? V equals F lambda, which equals 300 times 0.9, which equals 270 meters per second. Yeah? Now, I didn't say he was wrong. How do we get the time? Yeah? Yeah. Well, yeah, you can actually do it like a UVATS if you want, but the A is 0, it's not accelerating, yeah. So we can have here, what do I want? I want the time. And what do I know? I know the speed and I know the distance. So we can do the time for this piece here. So we can have, S equals U plus V over 2 multiplied T. But what's U? 270. And what's V? 270. Yeah, it's constant speed. So this would be 270, so then you get 100, yes, equals 270 T. So what does the T equal? It would be 100 over 270. But it has to do this twice, doesn't it? It has to go there and come back. So we'll just multiply this number by 2. Yeah, and what do we get? 0.74? Yeah. Sorry. 7407. Okay.
I have a question.
Yeah.
U and V is same.
Yeah, the speed doesn't change for a wave. We say, well, for now the speed doesn't change. We just say the speed is constant 270 meters per second. So the U and the V are the same. Yeah. No change of speed, no acceleration. Now of course, in the real world, it will change. Do you think the wave will get faster or slower in the real world?
Slower.
Why?
Just to lose some of its energy when it hits the wall.
Yeah, when the wave hits the wall, it will lose some energy. And also when the wave is moving in the air, it's slowing down, you know. If you think about it, if you're moving through something, you're going to always slow down. You're not going to keep getting faster. Okay. I think that's enough examples because really the lesson for the first lesson today is all about using this formula and some other ideas. So I'll let you try these for a few minutes. Some of these questions are just ideas, and some of these questions are calculations, okay? So, if you can try them all, most of them are calculations. Yeah. Try this for a few minutes. It shouldn't take you too long to do. Did I give you two? No. I actually did the first one for you. That was my example I did.